Hello and welcome to this video on how to conduct tests of means with the SPSS computer program. And so here is an agenda of what we will be covering today, and it looks like quite a bit, but hopefully you will see that part of it at least is review, so we'll be going over that, and then I'll be showing you how to do some of the tests of group means to go with that. So let's start off with reviewing graphs, how to make a graph. And if you go to the SPSS computer program, you'll remember that we click on graphs and then chart builder, and within chart builder there are a variety of graphs. First of all, a histogram here on the left hand side for a scale variable. We also have bar graphs and pie graphs for categorical variables, and box plots here on the left for ordinal variables that have 8 or more categories, or scale variables that are not continuous. So all of your favorite graphs can be made in Graphs Chart Builder. And so that's this right here. So let's go ahead and say we've covered that. The next thing is to review descriptive statistics, and for descriptive statistics we'll either want to make a mean and standard deviation for our scale variables, a median and interquartile range for those variables that aren't normally distributed, or for ordinal variables with 8 or more categories. And then for typical categorical variables, we would report an n and a percent. And what you'll notice is all three of these have analyzed descriptive statistics as their base. And so we'll just be doing something a little bit differently here on the end depending on what kind of variable we're analyzing. So let's go to, we'll cancel that. Analyze descriptive statistics, and for our first one we'll be looking at mean and standard deviation. Remember how SPSS tries to help you out, and so there's the symbol for mean and there's the symbol for standard deviation. So under descriptives you would choose whatever variable you want to test and move it over here into the variables box. For a median and interquartile range, we'll go to Descriptive Statistics Explore, and whatever variable we choose to put in there, we would go to Statistics and ask for percentiles. That'll get us our interquartile range. And then we can also ask for plots here. Remember, we can ask for a histogram. It automatically creates a stem and leaf plot and so forth. So we'll cancel that. And then for n and percent, we would go to Analyze Descriptive Statistics Frequencies. And here we can choose all kinds of different statistics for those variables as well. But this is the primary place that we would look for the n and percent, those frequency tables right here. That's exactly what we're asking for there. Okay, so that was a quick review of our descriptive statistics. So we've covered that. Now let's go ahead and look at what's new today, and that's our tests of group means, specifically a paired samples t-test, a one sample t-test, an independent samples t-test, and a one-way ANOVA. And so those are the 4 kinds of tests that I'm going to show you how to conduct. For the paired samples t-test, it's important to have data that is paired, and so I've brought up this improved sanitation data set that we have used in the past, and specifically I'm wondering perhaps how much the overall, remember national is a combination of urban plus rural, so I'm wondering how much sanitation for that country overall has changed from 1990 to 2015. And so in order to do that, I'm going to do a paired samples t-test. So I'll go to Analyze, Compare Means, and here's a paired samples t-test. And notice in the little symbol they try to show you that it's at time 1 versus time 2. And the thing that I'm going to do here in the paired samples t-test is I'm going to put those two variables in under variable 1 and variable 2. Now I like to put the after in first and then the before, and you'll see why when we get to the output. When this creates output, what it does is it gives us some descriptive statistics. We have a mean and a sample size and standard deviation and standard error for each one of those. So for 2015, the average sanitation was 75.877. For 1990, for those same exact countries, the mean was 66. Now you can see from 1990 to 2015 that has gone up. And what happens when I put the 2015 in first in that analysis is it shows this paired difference as a positive number. If I were to put them in the opposite order, this would be a -9. And for some people that can be really confusing because a negative implies that it went down over time. And so if you always do it the same way, then you won't have a hard time interpreting what this means. You might choose to do it the other way, and if you do, you're not wrong. You just have to remember that you're taking the before and subtracting the after, and so a negative number means improvement, or a positive. So the main thing to remember here is that you need to pay attention to the headers of these. Here with the paired samples t-test, we're looking at paired differences, and this is the mean difference that we're seeing. In other words, the average. So 9.3 was the average change for a particular country in terms of improved sanitation. This is the standard deviation of the differences and the standard error of those differences, and here's a 95% confidence interval of those differences. So we think that the difference between 1990 and 2015 is 9.3. We are 95% confident that the actual population mean of difference is somewhere between 7.5-ish and 11.3 or so. So those numbers, then we would want to see what the t-value is for that particular analysis. That's 9.7. If you remember, a t-value anywhere greater than approximately 2 usually becomes significant pretty quickly, and we have an adequate sample size for that. And so our p-value that goes with this t of 9.793 is less than 0.0005 or so. So that's a pretty significant p-value. We would conclude that there is a change between 1990 and 2015. The next thing that we are going to do, so that's the paired samples t-test. The next thing that we're going to do is we're going to need to calculate a BMI in order to run this one sample t-test. So let me go and get the data set that we'll be using, and this one is the YRBS for Wyoming in 2015, and you'll need to review what those variables are. Specifically, we're going to be using Q2, which is what is your gender, and here it says 1 is female and 2 is male, so those are our two options. We are going to be using Q6, how tall are you? Q7, how much do you weigh? And then if I scroll quite a ways down to Q77, we are going to use soda drinking. You'll notice the different categories here. Did not drink soda 1 to 3 times a week, 4 to 6 times a week, once a day, twice a day, 3 times a day, and 4 or more times a day. So those are the main variables that we will be focusing on for the analyses that you'll be running. So first of all, we know we have a how tall are you variable and how much do you weigh, but we do not have a BMI variable yet in this data set. So let's go ahead and create one, and the way you do that is by going to Transform Compute. Transform Compute, you can calculate all different kinds of things, and literally you would be essentially taking this, here's the height, Q6 is height, remember, and here's Q7 is weight. So this is height in meters, 1.57 meters, or 157 centimeters. Q7 is weight in kilometers, so 43. We're calculating BMI, which is kilograms, in other words 43.09 per meter squared, so divided by 1.57 squared. Now you could get out your handy dandy calculator, and for however many people in this data set, you could calculate 43 divided by 1.57 squared, 55 divided by 1.60 squared, 57 divided by 1.65 squared, and on and on and on, all the way down the, or you could ask the computer to do that, and that's what we're going to do in Transform Compute. So under Transform Compute, you bring up a new dialog box, and the first thing it asks you for is target variable. In other words, you're going to be creating a whole new column in your data set, and they want to know what would you like to name that. So I'm just going to name it BMI, keep it simple. And we know that this needs to be, and so BMI is equal to kilograms per meter squared, but the computer doesn't know which one is kilogram and which one is meter, so we're going to have to do the work there. I'm going to say Q7 is kilograms, and then I can click on divided by meters, and these, the double asterisk is taken to the power of 2, and so this will get you your BMI calculation. So kilograms per meters squared, and I'm going to go ahead and click on OK. And if I go to Data View and I scroll all the way over here to the right hand side of the data, you will see my new variable BMI, and you'll see that it's 17, 21, 33, 19, 47, 27, and so on. So these are the calculated BMIs. Really quickly, let me show you two more ways that you could have calculated BMI, and they would all be equally good. You could also take this and you could put parentheses around the bottom part of that equation in case you had a lot of things going on there. I'll call this BMI 2. And so let's go ahead and create that variable. And if we go to our data set, you'll see that those are side by side and it calculates exactly the same number. A third way is, let's say maybe you forgot about how to do the exponents, and so here we have BMI divided by kilograms divided by meters, and you can do meters squared is the same as saying Q6 times Q6. And for this one you must have the parentheses. If you don't have the parentheses, it won't calculate properly. So let's go ahead and calculate that one, and you'll see that that one calculated exactly the same numbers there. So here, let me show you what happens when you don't include the parentheses on that last style of calculating that. Basically what this does is it takes kilograms, divides by meters, and then multiplies by meters. And so you end up, whoops, I want to change this to 4 so that we'll see them all side by side. So if you divide by something and then multiply by it, it does this weird thing with BMI 4. So we don't want to do that. We want to calculate BMI in this fashion. So we ended up here with just kilograms, which isn't what we were after. So BMI 4 is actually wrong. The other three are identical to each other. Okay, so now that we've calculated BMI, let's go ahead and go on to the next one, which is to review the one sample t-test that we have done from before. And this is under Analyze, Compare Means, one sample t-test. And let's say we wanted to calculate, we wanted to see if the if the average BMI for this sample is equal to, so here's BMI right there. Let's say we want to test if the average BMI is equal to 22. Let's go 20. I'll click on OK. And here are the results of my t-test. This BMI is going to tell me what the average is. So here are my descriptive statistics, standard deviation, standard error. We have 2,277 who answered both of those questions for us to calculate the BMI. And then here's the one sample t-test. Here is the mean difference between our variable 22.9818 and minus 20. And so here's the difference between that, and here's the t-value and the p-value that go with that particular analysis. And remember, degrees of freedom is simply n minus 1. And so here's a 95% confidence interval of that difference. So we're saying that we tested if our group's average was equal to 20. We found that it was not, based on our t-value and our p-value, and we're 95% confidence interval, 95% confident that the population mean is somewhere between 22.9818 or sorry, 20 plus 2 or 2.784 to 20 plus 3.1797. So that's where we're confident that the actual population mean lies. So that's our our one sample t-test. The next one we're going to be running is independent samples t-test. And so for this one, we need to compare the averages of two groups. So let's say boys versus girls. Let's say we wanted to test whether the average BMI for boys and girls are the same. So let's go ahead and go to Analyze, Compare Means, Independent Samples t-test. And there is one new thing that you need to learn about in this one. First of all, we're testing whether the BMI is the same for two groups. And so this grouping variable, then I'm going to put Q2 in for the grouping variable. And here, since it's highlighted in blue and you can't click on OK no matter how hard you try, we need to define what those two groups are. And so this blue is a reminder to define those two groups. So click on Define Groups, and our first group is a 1. Our second group is a 2. We'll go ahead and click Continue. Now you'll notice that those 1 and 2, those numbers showed up here in my grouping variable, and I can click on OK. So go ahead and click on OK. And the Independent Samples t-test also gives you descriptive statistics here at the beginning. So the average BMI for females in our sample is 22.747. The average BMI for males is 23.2136. We can see that those numbers are different. And our hypothesis is, are those statistically significantly different? Now the actual t-test for equality of means is over here to the right hand side of this vertical line. You'll notice that separates the t-test for equality of means from Levene's test for equality of variances. And the reason that we do a Levene's test for equality of variances is that so often when we are running a statistical test, that assumption of equal variances is violated. And so the computer knows that, and so within SPSS they've automatically set it up so that we will have an answer to our hypothesis if the equal variances assumption is met, or if the equal variances assumption is not met. So if the equal variances assumption is met, we will use the top line all the way across, and if the equal variances assumption is not met, then we will use the bottom line. This p-value right here under Levene's test for equality of variances, 0.022, that p-value tells us if the variances are equal. Remember, this is one of the assumptions for our independent samples t-test. If the assumption is met, then this number would be greater than 0.05. and we would use the top row. Since this number is less than 0.05, that means it's down here close to the bottom. That means we're going to use the bottom row. And so the t-value to answer our hypothesis is negative 2.315. Now you'll notice that these two t-values are actually pretty close to each other, and that tells me that my variance assumption being violated really isn't that bad. In fact, if you look at the standard deviation and the standard error, those actually look pretty close to each other. So even though this Levene's test for equality of variances says that the variances are not equal, that's probably because of our large sample size. When you have a large sample size, it's very sensitive to small differences. And so these two numbers for the t-value are going to be pretty close to each other. The p-value is actually exactly the same, 0.21 either way. And so the probability of that happening. Over here on the right hand side, you'll see we're looking at the mean difference between those two values, 22.7 and 23.2. Those are kind of close to each other, but they are, according to our test for equality of means significance level, or p-value, they are statistically significantly different from each other. And here's how different. Here's a 95% confidence interval of how different they are from each other. So anywhere between 0.86 and 0.07. So that is a summary of our independent samples t-test. And specifically, I needed to point out to you that Levene's test for equality of variances. If the p-value in summary is less than 0.05, then we conclude that the variances are not equal. This Levene's test tells you absolutely nothing about your original hypothesis about whether males and females have the same average BMI. This Levene's test p-value, 0.022, only tells you if the variances for men and women are equal or not. So that's a very, very important point. People get this significance confused with the significance for the actual t-test. And in this example, they look like they're pretty close to each other, but often they are very, very different. Okay, so that was our independent samples t-test. And lastly, we have a one-way ANOVA. So let's go ahead and take a look at what that one-way ANOVA, how to run the analysis for that. We are going to go to Analyze, Compare Means, One-Way ANOVA. And this dialog box has even more interesting information. First of all, we are testing whether the average BMI is the same for different categories of soda drinkers. And the soda drinkers variable is this Q77. So we are going to put the BMI as the dependent variable and Q77 as the factor. So this is the one that breaks the data set into categories, and the BMI is the scale variable that we're testing. Now there are some other things that we need to add to this analysis. A one-way ANOVA analysis only gives you the F value, the one-way table. It only gives you the F and the P value that go with that. In all these other tests, we automatically got descriptive statistics. Not so in a one-way ANOVA test. So under options, we need to ask for descriptive statistics. We also want to ask about equal variances. Homogeneity is another word for equal. And so we're going to run an equal variance test, similar right here where it says Levene's test for equality of variances for the independent samples t-test. We're going to ask for that equal variances test to see if our variances are equal. And if they are not, we can click on either the Brown-Forsyth or the Welsh. I like this one better. In order to this Brown-Forsyth is the equivalent to the bottom row on the independent samples t-test. If the variances are not equal, it gives us the F value and the P value automatically. So let's go ahead and click that. I also like to look at a means plot, even though you've probably already done some other descriptive statistics that go with it. It's just a really simple click, and you'll be able to see a plot of the means for each of the different categories. Now, if we find in our analysis of our one-way ANOVA that the groups are in fact different, we want to know which groups are different from which other ones. And also our data that's automatically generated does not include that. So I need to specifically request post hoc test. Post hoc means after the fact. So after I've done the overall test, I want to find out which groups, by multiple comparisons, I want to find out which groups are different from each other. Now you can see that there are a really wide variety of different ones. Every statistician probably has their favorite. I'm going to stick with the ones that your textbook talks about, the least significant difference, in other words, an uncorrected p-value, and then the Bonferroni, which has the Bonferroni correction. If you had equal variances not assumed, you could select some down here, but we're not going to get into that much detail. So we have asked both for post hoc comparisons and options under the one-way ANOVA. So if your output does not look like what you see here, then you may not have selected the same things that I did. So we're testing if the average BMI is the same for each of the groups within soda drinking, which is the Q77. So let's go ahead and click on OK, and here's the output that we get. First of all, remember I asked for descriptive statistics, and here are the 7 different categories: soda, 1 to 3, 4 to 6, once, twice, 3, 4, or more. So those are my different categories, and here are the averages for each of those groups, and this is average BMI. So see how this table says it's a BMI table. So the average BMI for these students in this particular sample was 22.6327. So if they did not drink any soda or pop, their BMI was a 22.6. We'll say round to the nearest tenth. You could round to hundredths too. That would be good also. If they drink 1 to 3 times a week, their average BMI was only slightly higher at 22.76. If they drank soda 4 to 6 times per week, that's their BMI went up to 23.02. If they drank a soda every single day, once a day, their average BMI was 23.55. Now the other thing that you should probably notice is the number in each of these groups. The largest group was 1 to 3 times a week. There are 832 of them out of the 2,000 or so that were in this category, and another 375, so approximately half, drank soda 1 to 3 or 4 to 6 times per week. So you can see how the BMI gradually creeps up, and then an interesting thing happens here. At 4 or more times a day having soda, the BMI actually drops back down. And I'm going to scroll down to the graph because I think it's worth seeing right now, those averages in visual form. And so here's our 22, 22, 23, and so on. And we see that go up at the time when we have 3 times per day or more, and then suddenly with the 4 or more times per day it drops down. That group also was the smallest group, the 4 or more times per day. There were only, the 3 times per day was the smallest, and then the 4 or more times per day was the second smallest. So those two groups were the smallest. So their estimates are the most unstable. In other words, if we had one more person be added to that group, it could affect this mean. Whereas if you add one more person to a group that has 800 in it, it is less likely to greatly impact that mean. So it's not that it'll impact it a lot, but it's more likely to impact these smaller groups. So here's the test of equal variances, and this p-value tells me that the variances are not equal, and I'm not surprised with a sample size of 2,220 that my sample standard error or standard deviations are not the same. standard deviations in this case. And what I see is standard deviations that go anywhere from about 4.5 up to 7.1. Now remember, our rule of thumb is if they were double, then we might be starting to get into problematic areas. So this is not double. 7 is not double than 4.5. However, because we have such a large sample size, this Levine's test of equal variances shows that the variances are significantly different from each other. So they are, with a large sample size, it's very sensitive to small differences. And so you're almost always going to get this p-value less than 0.05 if you have a large sample size like this. The third piece of output in our ANOVA table, or our ANOVA output, is the actual F statistic and p-value to go with that. In other words, this F statistic tests whether the average BMI for all 7 groups are the same. And based on this F value and this p-value, we can conclude that they are not. And we don't know which ones are different from which other ones. All we know is that at least one of them is different. Here's the same, like if we were to look at the robust test of equality of means, in other words, this would be the equivalent for unequal variances, our p-value gives us the same conclusion. It's still less than 0.05. And so we would conclude to reject the null, whether we use the regular one-way ANOVA or the Brown-Forsyth test. Now, if we were to come down here to multiple comparisons and say, now I want to see which groups are different from which other ones. With the least significant difference, then this does not do a correction factor for having multiple comparisons. And so this is our most sensitive. In other words, we'll find the most differences with the LST test. So did not drink soda compared to 1 to 3 times a week, looks like that they're not different from each other. The did not drink soda compared to 4 to 6 times a week is also not different, 0.218. The did not drink soda compared to once a day, that is significant in this particular multiple comparisons, as is 2 times a day and 3 times a day. However, it's not different than 4 times a day. And so remember how it dropped down? That average dropped back down, and so it does not show that it's significantly different. You'll also notice the asterisk here next to the mean difference. And if we scroll down to the bottom of this table, it will say that the mean difference is significant at the 0.05 level. So we can literally just look for the asterisks. Now, we have looked at did not drink soda or pop compared to all of the other 6 categories, but we could also take 1 to 3 times compared to the other 6 categories. Now, the did not drink soda compared to 1 to 3 times a week is the exact same as 1 to 3 times per week compared to did not drink soda, but we haven't compared 1 to 3 times a week to the other 5 categories yet. And so you can see the p-values for those, and you can see that some of them are significant at the 0.05. And so you could do that for all of the different possible categories. Once we get down here to the middle part of the graph, this is where the Bonferroni starts, and it does the exact same comparisons all over again. And you'll see that this corrects for multiple comparisons, so it's a lot harder for those comparisons to be statistically significant. So did not drink soda is only different from 3 times per day, and the 1 to 3 times a day is only different from 3 times per day. So those are the only 2 comparisons that are statistically significantly different at 0.027 and 0.044. So that's a way of finding out, once you have an overall significant test, which groups are they that are actually different from each other. Here you'll see the schematic again of drinking soda, and that concludes then our one-way ANOVA test. So I showed you the post hoc and the options that go with that. The very last thing that I'd like to show you is the graphs for tests of group means. And so we've kind of come full circle here, and now I'm going to go to Graphs, Chart Builder, and I'll go ahead and create some of the graphs that are new to you. Under histogram, there's something that looks like a side-by-side histogram, and I'm going to go ahead and drag that up here. Let's say we want to split this variable by gender. Let me drag that over. And I'm going to look at our BMI variable that we have just now created. So this is going to create a histogram on the left for one of the groups and a histogram on the right for the other group. And so what that looks like is the histogram on the left is for female and the histogram on the right is for male. And you'll see the frequencies and also the BMI. So if you were to turn your head to the right or to the left, you would see this kind of as a histogram. And you can see that it does look like this area in here is a little bit more filled in for the males. So that's kind of an interesting way to look at this data. You could also create individual histograms. That wouldn't be wrong. Play around with the chart builder a little bit. You'll notice all kinds of different things that you can create. One of the things that I like to create is kind of a simple scatter plot of different variables. So let's say we have our BMI variable that we would like to look at by the soda drinking. This is one way of looking at it. And basically this will create vertical lines of dots because we can't really create multiple histograms side by side. They don't really look right. Since we have so many data points, they all kind of mush together, but you can kind of get the idea if you were imagining these to be histograms that the bulk of this is somewhere between, for most of the variables, somewhere between about 19 or 20 and going up to about 30-ish. As you get farther to the right, you'll see the dots a little bit more spread out, and that's because these samples have fewer people in them. The ones over on the left have a larger sample size, and so you get a little bit more. You can see the individual circles over here. So that's another thing that you can look at. Your textbook really liked showing you side-by-side box plots, and so we could look at that in terms of the different categories and the BMI. So let's go ahead and do that. Here's what those different categories looked like, and so you can see the interquartile range and the median, as well as the whiskers kind of go out to 1.5 times the width of the box times the interquartile range. And then another 1.5 includes the little circles above, and beyond that, so those are considered to be outliers. Beyond 3 width of the box are the little stars, and those are considered to be extreme values. And so you get a real sense of the actual data here. Where specific individuals are. They're even labeled by their ID number. So if we were to go specifically to line 74 in our data set, we would find this person who drinks soda once a day, and they have a BMI around 39 or 40-ish. And so we would find that specific person. We could find all of these specific people based on their ID number from the data set. So those are some graphs where you can look at tests of group means for all the groups on the same graph. And so now we have looked at all of the things down here. So we're done. Thank you for joining me for this tour of tests of means with SPSS.